Okay, Chapter 6, Discrete Probability Distributions. All right, so in this section, we will learn about discrete versus continuous random variables. We'll be able to identify discrete probability distributions, graph discrete probability distributions. We're going to compute and interpret means of discrete random variables. We're going to interpret the mean of a discrete random variable as an expected value. And then finally, we're going to compute the standard deviation of discrete random variable, right? So this chapter, chapter 6, focuses on discrete random variables. And then beyond chapter 6, everything else is going to be continuous random variables. So really just this chapter is going to be on discrete random variables. And really there's only two sections. It sounds like a lot saying this chapter. It's really just two sections that we're going to be focusing on. Chapter 7 also just has two sections we're going to be focusing on. And chapter 8, I think, also only has two sections. So there's not a lot of sections per chapter, but there's a lot of content. They're very dense material. So make sure you pay close attention, make sure you read the book, do your homework, and prepare for our exams. Okay, so the first thing we need to do is establish the difference between a discrete versus a continuous random variable, right? Like I said, this chapter focuses on the discrete ones, and in the next chapter and beyond, we'll be focusing on the continuous. So just in chapter 6, we use discrete random variables. Keep that in mind because the formulas that we come up with apply to just chapter 6 questions, right? A very common thing is that students take the ideas and the formulas that we work with in chapter 6 and push them through to the other chapters, right? So that's not going to be valid. All of the stuff we learn in chapter 6 only applies to discrete random variables. Okay, so what's the difference between them? What's a discrete random variable versus a continuous one? Okay, first of all, what is a random variable? A random variable is a numerical measure of an outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as capital X. Okay, so we have some sort of experiment, and that could be something like you roll a six-sided die. Or it could be that we have a deck of cards, 52 is the standard deck of cards. We have a deck of cards, and we're just going to shuffle them up and randomly pick one of them and look for something in that card. Maybe what color is it? What suit is it? Is it a 3? Those kinds of questions we'll ask. Right? So that could be an experiment. Draw one card from a 52 card deck. The experiment very often, especially for us, is something really simple. Just a survey. You randomly stop somebody on the street and you ask them something. Maybe you ask them, what is your shoe size? What state were you born in? Just some piece of information that you randomly get from people. That's an experiment. Okay, so if we think about before you actually execute the experiment, you start thinking about what you're about to do, and you think about the types of answers you'll get from people, right? Once you ask them this question, or the types of results you'll get from doing the experiment, right? So if I roll a six-sided die, what are the types of things can I get? Well, it could be a 1, it could be a 2, it could be a 3, right? If I stop people and I ask them, what state were you born in? Of course, I can, possible answers are California, Oregon, Washington, right? But then I also have to kind of think about the possibility that they tell me something unusual. So I have to insert there an other, perhaps. Or maybe think about a couple of options. Maybe they were born on a military base in another country, in an embassy in another country. So, kind of think about all the possible outcomes of what you will get. Okay. Those outcomes, those results, the types of answers that you get, that's what we're going to be analyzing. And those types of results are going to fall under a discrete or a continuous category, right? So the discrete random variable has either a finite or a countable number of values. Finite or a countable number of values. So if I ask people, hey, what state were you born in? And of course, I keep in mind that maybe I list all 50 states, and then I put an other at the bottom, and I don't really care. Anything other than that, or if you're born outside the US, you're part of the other. So I've accounted for everything. That means I have exactly 51 possibilities when I stop people and I ask them, randomly stop people on the streets or somewhere, and I ask them, hey, what US state were you born in? I have 51 possible options. That's a discrete random variable. There are only 51 options. Good. Maybe I ask them, how many siblings do you have? Right? So I stop them and go, hey, how many siblings do you have? Maybe they say 0. They're an only child. Or they say 1 brother or one sister, or 2 or 3 or 4. There might be a lot, right? Of course, now we have to be very, very careful about what we define as a sibling. So some people might come up with weird things about, half brother, half sister, brother-in-law, all kinds of things. So let's be very specific about what we mean by a sibling, so that we can be clear on what kinds of results we will accept. And so it's reasonable that maybe someone might say 2 or 3 or 4, and maybe up to a lot, maybe 20 or 30 or 40. So it might be a large number, but it's definitely not infinite, right? No one's going to say I have 45,742 siblings. And even if they said that number, that's even that's not infinite, right? So they won't say an infinite number. They will say a finite number, most likely a reasonable number, which is relatively small, right? So there are types of questions that you can ask where the outcomes are finite and countable, and the outcomes are not necessarily numerical in nature, right? So like I said, the states, right, they're not numerical in nature, but I can count them, right? I can assign a number to them, right? Once I take back the information back to my lab so I can crunch things out, I can encode each state that people said with a number, right? California, 1, right? So whenever somebody said California, I'm just going to write it down in my data as they responded 1. Or if they said Nevada, okay, Nevada, I'm going to encode it in my own data so that Nevada is 2. Whenever anybody says that we're born in Nevada, I'm going to encode it as they responded to 2. Good. And so on and so forth. So I can index the categorical data, the non-numerical results that I get. I can encode them by a number, and the results are finite. So therefore, it's a discrete random variable. Okay. So in this class, I know it's starting to sound like it's a little complicated, but keep in mind this is just an introductory course. We're not going to make it too complicated. In this class, we mostly focus on simple things like rolling a 6-sided die or withdrawing a card from a standard 52 card deck and asking something about it. What suit is it? There's only 4 suits, so we can encode that by 4 different possible options. Or maybe I might ask, what color is it? And we can encode that by 2 possible answers. It's only red or black, right? Okay, well, what isn't a discrete random variable? Well, that's a continuous random variable. A continuous random variable is a case where you ask a question and the outcomes, the possible answers that people can give you, are just absolutely infinite. There's no way to even prepare for the possible outcomes that people can give you. Keeping in mind that we have to imagine that we are not limited by measuring technology. So, for example, if I randomly stop people and ask them, what is your weight? Okay, weight is something that that is often limited by the technology we use, right? If you use a scale, like an old school scale that just has the little guys, here's a scale, right? And you stand on it, and here's this little window thing. If you have the kind of scale that just has these little like arrow thing, right? It just like rolls around in there. It's mechanical, and it just kind of lands on a number. For me, that number might be in the neighborhood of probably 190, if I'm honest. I used to be 170 something, but then COVID hit. So thank you, COVID. I'm in the neighborhood of 190-ish. All right, so that's what I weigh. Okay, but then if I go over to a more fancy scale, it'll be a digital one. and that digital one might be able to go out to several decimal places. So a more accurate answer might be that I'm 190.74. Maybe it goes out to 2 decimal places. Okay, so I'm doing, I have a little bit more accuracy. If someone stops me on the street and says, how what's your weight? I could just say 190, but to be more precise, I could say this one. Or if I, go over to the physics department, they have some fantastic, very, very accurate scales, right, for industrial purposes, and they go out to several decimal places. So if I go stand on one of those scales, I might find out that no, actually I'm 190.73821, even more accurate. Okay, so what we want to do here when we're trying to decide if something is a continuous random variable or not a continuous random variable, we want to imagine that there is a very special piece of technology, some alien technology not available to us yet, that is infinitely accurate. There is no such thing as rounding. It gives you the exact answer out to as many decimal places as is needed. Now, when I say as is needed, is because it's possible that this is my exact weight, right? Maybe I get on this magical alien machine that is super, super duper accurate forever, and it might be that my weight is 190.738210000 forever. Maybe that is exactly my weight. I don't even if I have a more precise scale, maybe that's my weight. Or really, maybe my weight is exactly it's possible your weight might be exactly 190.0000000 forever. That might be your weight, right? So it's just because you have access to this infinitely accurate scale doesn't necessarily mean you'll have an infinite number of different numbers rolling around here, right? So it might be exactly this. Okay, so we want to imagine that we have this piece of alien technology that is absolutely perfect. There is no rounding, and it'll go out as far as it needs to go, as far as accuracy is needed. Okay, so given that we have that, now think about the possible answers you can get when you randomly stop somebody and ask them, what is your weight? Well, there's just so many, right? There's an infinite number, right? That's the density of the number system, right? Just when you think that you've listed all the numbers, 1, 2, 3, it turns out that because of decimals, fractions, there's more, right? Between 1 and 2, you're like, okay, well, how about, we can always put in the 1.5, 1.5. And between 1 and 1.5, well, we can always go in the middle. Go, okay, well, how about right in the middle? That's 1.25. Like, okay, well, what about in between those two? We can go right in the middle between those, right? So whenever we think that we've listed all the numbers, there's another one in between, right? Always and forever. So even just between 1 and 2, there's an infinite number of values just in between those two, right? So it's very dense, the number system. And that's what a continuous random variable is. It's going to be an experiment where the possible outcomes of that experiment are so vast, so diverse. There's so many possible options that they can only be considered as infinite, and so therefore it's a continuous random variable. Okay. When we want to identify them, think about how we know that answer. If we know the answer, right, what's your weight, for example, we need some sort of technology, and that technology is limited, right? What other things are limited by the technology you use? For example, your height, right? If I kind of just put myself up against the wall and kind of measure myself and get a pretty good guess, okay, that's a pretty good guess. But if I go to the doctor and they have that special machine thing, that thing's a little bit more accurate. And again, if I really want to be more precise, I can go over to the physics department and use lasers or something and really, establish exactly how tall I am. So, little things will make a big difference if you want to be super accurate, right? I don't know if you guys are aware, our actual height changes. It varies throughout the day, not just because of our shoes. That's an obvious, easy one, of course, if you're wearing different types of shoes. But even if you don't include that, our actual height varies a little bit. When you have a nice long rest at night and you sleep, probably in a bed horizontally, you don't have gravity pushing you down for a good 8, 10, 12 hours, and so your body will actually stretch a little bit more. So right when you wake up in the morning and you stand up and measure yourself, you're going to be a little bit taller than you will be after several more hours of gravity squishing us down, right? And so gravity has an impact. Well, therefore, when gravity is a little bit stronger, we're going to shrink a little bit more, and when gravity is a little bit lighter, we're going to be able to grow a little bit taller. Recently, we had an experiment. NASA conducted an experiment where astronaut Kelly spent, I think, about a year in outer space, and we really wanted to measure and see what was happening to his body while he was in outer space for a year, and lots of stuff happened. And then we were able to compare that and contrast it with his twin brother who stayed here on Earth. And one of the things that happened is that he grew taller. He spent a year in outer space. He didn't have gravity pushing him down, and so he grew a little taller, right? His bones stretched, everything just grew a little bit taller. But then when he came back to Earth, that gravity kicked back in and started squishing him back down to his previous height. And of course, there's a lot of long-term medical consequences to doing that to your body, right? So it's pretty tough to go into outer space. People don't understand the complexities that go into having a human body be away from the surface of the planet where we're comfortable. We're made to live here. We're a species that has developed to be in this comfortable little place on Earth, and it's pretty hard for us to go anywhere else. Anyway, so anything that gets measured, like height, weight, anything involving time, right? I mean, how do you measure the speed of a car? Well, it involves time. You have to be able to see how much distance was traveled in a time elapsed. Well, how accurate was your clock? How accurate did you measure that distance? Right? So all those things are going to be continuous random variables. Okay. Again, it sounds really complicated, and it can be, but in this section, it's not going to be that difficult. We won't let ourselves go into the deep end of things. This is just an introductory course, so try not to let this scare you off too much. Okay? So, discrete random variables are cases where the experiment has a predictable number of outcomes, right? Before you even do the experiment, you got to think to yourself, what's going to happen? And if there are a predictable number of outcomes that are usually very small and finite, that's a discrete random variable. Classic example, think of rolling a 6-sided die. A continuous random variable is a case where you're going to do an experiment and the possible outcomes are just absolutely infinite, right? I'm going to, control Hubble telescope, and I'm going to randomly have it point to some star somewhere. What are the possible outcomes? Well, that's infinite, So, well, not quite infinite, since there are, that's not a good example, right? We do have some estimate of the number of stars, and it's not infinite. It's just really, really, really big, right? Last I heard, it was in the neighborhood of 100 billion galaxies, and each galaxy has about 100 billion stars, and each star has several planets. So they're just really large numbers, but not quite infinite, at least for what we can see, right? The visible part of the universe. And okay, I digress. Anyway, so height or weight is the standard, go-to example about a continuous random variable. You randomly stop somebody and you measure their height up to a very infinitely precise level, within an infinitely precise device. That would be a great example of a continuous random variable. Okay, some examples. All right, determine whether the following random variables are discrete or continuous. State possible values for the random variable. Okay, so the number of light bulbs that burn out in a room of 10 light bulbs in the next year. Okay, so I can imagine a whole scenario for why this would be important. So for example, let's say that you subcontract the maintenance of a building to another company, right? So you work in an office building, and instead of having a dedicated staff dealing with the maintenance of the building, you subcontract it to another company. And that company comes in, and one of the things that they do, for example, is put light bulbs in every room. So they're interested in knowing how long are those light bulbs going to last, right? So if they put in brand new light bulbs, there's 10 light bulbs in this room, how many of those light bulbs are going to go out, just kind of burn out naturally within the next year? 1 year later, they're going to come back to this building, go back to that room, and count. So let's see, it turns out that within 1 year, maybe 0 of them burnt out. That would be fantastic for them. They don't have to do anything, right? Or maybe within 1 year, only 1 of them burnt out. Or maybe 2 out of the 10, or maybe 3 out of the 10. So what are the possible outcomes of this experiment, right? You put in your light bulbs, and maybe 1 year later you come back and there are 0 that burnt out, right? N is the number of light bulbs that have burnt out. So maybe 0 have burnt out. Or maybe exactly 1 burnt out. Or maybe 2, or maybe 3, or maybe 4, or maybe 5, or maybe 6, or 7, or 8, or 9, or maybe all 10, right? How many outcomes are there? Well, remember, we like to count starting with 1, so usually, people say 10 options, but that's because we start counting here, right? We usually start there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but then we got to come back over here and count this one. So even though there's only 10 light bulbs, there's actually 11 options. Keep that in mind, that we often have to go 1 more because of the 0. Okay, so there's 11 options. And this might be an interesting question because perhaps the contract, right, you're subcontracting out your work to a maintenance company. Maybe your contract says, if 1 burns out, no big deal. If 2 burn out, it's okay. But maybe once 3 or more light bulbs burn out, you insist that they come down to your building and change the light bulbs, which is kind of a big deal for them, of course, because they probably don't have a person from their company in your building just sitting around waiting to do something, right? They have to put in a maintenance order, right? That's what happens in my apartment building. If something needs to be fixed, I got a call, they put in a work order, and then somebody has to travel all the way across the city to get to my building and come inside and fix it. So they don't want to do all that work just because 1 light bulb burnt out in 1 room. But if maybe 4 light bulbs burn out, well, now it's kind of a dark room, right? Now we need them to come and do it. So they might be interested in that. What is the likelihood that 4 out of the 10 light bulbs burn out in 1 year? Right, so that's the kind of question we'll be dealing with. But for now, we're just identifying what's a discrete random variable, what's a continuous random variable. Okay, the number of leaves on a randomly selected oak tree. Okay, so we're biologists, botanists, and we're studying something about oak trees and the number of leaves, and who knows what we're doing. But we want to count the oak leaves. So our experiment is we're going to randomly go into the forest. We're going to randomly pick one oak tree, and poor thing, we're going to chop it down. We're going to really, really, really study it to a point where we're going to take every little leaf and we're going to count them, right? So once we chop down this tree, here's these sad little leaves. Wow, that's a terrible I'm the worst drawer. I have no idea how to draw a leaf. I don't know. Does that look like a leaf? Oh, wow. I'm pretending that's a leaf. Okay, so that's leaf number 1. Okay, and then we go over and we go, okay, let's take another leaf, right? It's a very, very tedious process here. This better be a really important project. I don't know. Here's leaf number 2. Okay, and we keep going. How many leaves is this oak tree going to have? Well, it's going to have a lot, right? Probably thousands, perhaps tens of thousands of leaves. I have no idea. But it's not going to have an infinite number of leaves. And even though it takes a long time, I can count them, right? I can, maybe this is my thesis project to graduate from UCLA and be a botanist. And that's what I got to do. If that's what I got to do, then I'll do it. I will write down, I will categorize each individual leaf, I will label it, I will maybe put each one in a tiny little baggie and really expand the whole thing out. Or maybe there's something really important about this tree. Maybe it's like the last tree of its kind that we know anywhere on the planet. And of course, humans, we decide, oh, I know, it's the last tree. Let's chop it down and count the leaves. Who knows? Maybe we want to keep it for scientific purposes, right? So there might be some good reason why. Anyway, there's 1 leaf, 2 leaves, 3 leaves, dot, 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 dot. So lots of leaves, sure, but definitely not infinite, right? So when I think about my possible values, is it possible that there are 0 leaves on this tree, right? I'm going to randomly go into the forest, and without even looking at the trees or anything, I'm just going to randomly pick one. I'm going to have my GPS randomly pick a tree, and I walk into the forest, here's that tree. It's possible that it's got no leaves in it. Great, makes my job of counting leaves super easy. It's possible that there's only 1 sad leaf on it. Maybe there's 2, maybe there's 3, maybe there's 4, dot, 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 right? But it's definitely not infinite. I know that it's not going to just go on forever and ever and say, oh, it's infinite, it's billions. No, it's large, but not infinite. Good? These 2 are both discrete. Both of these are cases that describe a discrete random variable. This one is discrete and very small, really. It only goes from 0 through 10. There's only 11 options. This one is discrete, even though it's very large. It's going to go up to a big number, maybe thousands or tens of thousands, but it's not infinite. So it's a large number of outcomes, but still countable. It's doable. So it's discrete. Okay. Now, on the other hand, let's look at this one. The length of time between calls to 911. Time, the length of time. Well, first of all, you got to ask yourself, how accurate is the device I'm using to test this, right? Am I using, an old school clock with the little hands? Am I using a digital clock? Am I using an atomic clock? How accurate? How many decimal places does it go to? And so for the purposes of deciding whether it's continuous or discrete, we got to think that we have this alien technology thing that is super, super duper precise out to infinite number of decimal places, as many decimal places of accuracy as is needed, right? So, for example, we have call number 1. Someone calls 911. And just because they call 911 doesn't mean it's an actual emergency. Lots of stuff being called them 911. Could be something like, I'm calling 911 because I'm reporting something. Maybe I'm reporting that a fire hydrant is leaking water. Call 911. All right. Or maybe I'm calling because my neighbors are making too much noise and it's late and I gotta create a video in the morning. Yeah, I'm that guy. Okay, so here's call number 1, and it comes in at a particular point in time. Here's a timeline of time. And here's call number 2, the next call right after that one, call number 2. Somebody else calls right over here. So how much time elapsed between calls, between 911 calls? Is this gap between the 2 calls 3 minutes and 4 seconds? Okay, maybe that's what it is. Or is it, well, okay, well, when we get a more precise measuring device, we see that it wasn't really 4 minutes and 3 seconds. It was 4 minutes and 4.025 seconds, right? And you see where this game is going. So how accurate is this, right? It might be even more accurate if we have a device that can measure that, can detect that. So the number of possible answers of how much time can elapse between two calls, it's absolutely infinite, right? So now that I've got call number 3, I start the timer, right? Here's my experiment. I start my timer, and I start counting how much time goes by until the next call comes in. Can I predict what the possible outcomes are? Not really. Maybe it only takes seconds. Maybe it takes hours. It might take days. Who knows? In very remote parts of the country, I imagine there might be a 911 call center where a huge amount of time goes by before anybody else calls in to the 911 center, right? Maybe hours and days go by before 2 consecutive calls happen. Okay, so this is definitely a situation where that deems or that calls for a continuous random variable, right? This one is a continuous one. Continuous random variable. Like I mentioned before, the continuous ones are going to be the subject of Chapter 7 moving forward. But for this section and the next section in Chapter 6, we focus on discrete random variables. So let's see the answers. Oh, okay, I should have pointed out that, if we let n represent the number of possible answers, okay, 0, 1, 2, 3, and if we let any variable, how about a, doesn't matter what letter you use, a represent the time, let the variable a represent the time between 911 calls, then that time could be anything strictly greater than 0. Good. All right. The probability distribution of discrete random variable x provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. Okay, so a probability distribution is kind of like a cheat sheet. It provides all the possible outcomes of your experiment, right? So it's different from actually executing the experiment. It's before you do the experiment or an analysis after everything is done, but it's a table or a graph or a formula that describes all the possible outcomes. And then next to it, it tells us the probability that that outcome is the result of an experiment, right? If you execute the experiment one time, what's the likelihood of each one of those? So, for example, let's say that you want to ask people's political affiliation, and you just randomly stop people and you ask them, what is your political affiliation? And you limit it down to a certain number of options, right? They can be a Republican, they could be a Democrat, they can be a liberal, they can be, other. Let's just say we just limit it down to those 4. Sorry if you're one of the people like not listing and clumping into an other, but at any rate. So you have 4 options there. So in your little cheat sheet, you list down all possible outcomes that somebody might respond. And then next to it, you would put down the likelihood, the probability that when you randomly select somebody, that they're going to choose that option, right? So that's a probability distribution. Part of the work we do in this section is to create those, come up with those distributions. And part of it is to be able to work with one that is given to you. So sometimes in your homework, a probability distribution will be given to you, and sometimes it'll be your job to create it, come up with it. Okay. Now, a probability distribution has to have a couple of rules that it must obey. Okay, so rules for discrete probability distributions. Let P of x denote the probability that the random variable capital X equals lowercase x, right? So this capital X here is a little bit different than this one. Then it must be true that the sum of the probabilities equals to 1, and it must be true that each of the probabilities is between 0 and 1, right? We'll see examples of this now, actually. So here's an example of, here's an example of a potential probability distribution. So here we have something where the possible outcomes are 0, 1, 2, 3, 4, or 5. Maybe this is a case like the light bulbs. Maybe there is an office that has 5 light bulbs, and we want to think about what is the probability that in the next year none of the light bulbs burn out. Or maybe within the next year, one of the light bulbs, exactly one light bulb burns out. Notice that I'm not pointing out which of the light bulbs we're talking about, right? I'm not identifying which one. I'm just saying one of the 5 light bulbs burns out. Or maybe 2 out of the 5, or 3 out of the 5, or 4 out of the 5, or maybe all 5 burn out, right? And then next to it, I have associated probabilities. So the way this is interpreted is to say that there is a 16% chance that none of the light bulbs burn out, right? 0 out of 5 light bulbs burn out. There is an 18% chance that within the next year, exactly 1 out of the 5 light bulbs burns out. There's a 22% chance that exactly 2 out of the light bulbs burn out. There is a 10% chance that exactly 3 out of the 10, a 30% chance that exactly 4 out of the 5, and there's only a 1% chance that all 5 of the light bulbs burn out, right? That's what this is describing. However, we have to keep in mind that for it to be a valid probability distribution, these 2 rules must be satisfied. Now this rule, the second rule, indicates that each probability must be a value between 0 and 1 inclusive. Okay, that should sound familiar. And that is true here. Each one of these are valid probabilities between 0 and 1 inclusive. The other criteria is that the sum of those probabilities must be equal to 1. So now if we add all of these values, 16, 18, 22, right, let's see, 18 and 22, that's easy, that's 40, that's 50, that's 80, that's 96, 97, right? These add up to 97. So it fails that criteria, right? This needs to be equal to 1, and it's not. It fails to be equal to 1. So that means that this is not a proper probability distribution, right? Not a proper probability distribution. Right? Because they don't add up to 1, it just begs the question, what about the other 3% of the time? Right? That's what's missing, because they only add up to 97. So 16% of the time, 0 out of the 5 light bulbs burn out. 18% of the time, 1 out of the light bulbs burn out. Okay, so then there's a missing 3%. 3% of the time what? We've already covered all possible outcomes. There's only 5 light bulbs in this room. I can't burn out 6. There's only 5 in there. I can't burn out a negative number of light bulbs. I can't burn out a decimal number of light bulbs. So it just begs the question, what is that? 3% of the time, what happens? So it just doesn't make sense for us to have something that only adds up to that. Okay? All right, let's look at another one. Let's say this time somebody creates this as a distribution for your 5 light bulbs in a room. So now this is saying there is a 16% chance that within 1 year, 0 out of the 5 light bulbs will burn out. There's an 18% chance that within 1 year, 1 out of 5, exactly 1 out of 5 of the light bulbs will burn out. Okay, but then if we come back down here, what in the world is this? We can't have a negative number of light bulbs, right? I'm sorry, we can't have a negative probability. It doesn't make any sense. So that rule has been violated, right? We cannot have this. We can't have a negative. It doesn't make sense to have a negative probability. You have a negative 1% chance that 5 out of 5 light bulbs will burn out. That just doesn't make sense. So right off the bat, I don't even have to bother adding them. I know it already fails to be a proper probability distribution, right? So this one also fails. Not. All right. And finally, maybe this third option works out now. So here we have again 5 rooms in a 5 light bulbs in one room. You leave, you come back 1 year later, 365 days later, and you count how many of the light bulbs went out. Maybe 0 out of the 5, maybe 1 out of the 5. Okay, and then we have the corresponding probabilities associated with them. Each one of these probabilities is a valid one, right? Each one is between 0 and 1 inclusive. It makes sense. This is saying that there's a 22% chance that when you come back 1 year later, there will be exactly 2 out of the 5 light bulbs burnt out. This one's saying that there's exactly a 30% chance that exactly 4 out of the 5 light bulbs are burnt out 1 year later, right? And then if we add up all of these probabilities, they should also work out, right? And just to kind of group them up to make life easy, let's see, this one is going to be 40, 40, 50, 80, and then 96, 100. They add up to 1, right? You can just get your calculator and add them up. So we see that both conditions have been satisfied. The sum of all of these equals to 1. The sum of all of them equals 1. And each probability is between 0 and 1 inclusive. So finally, we have a proper probability distribution. This one is a proper. It's a good one, right? It's not the only one that can work. Obviously, we can move these numbers around, or these numbers can change a little bit. But it satisfies both conditions, so this is something that could be a valid probability distribution for a situation. Okay, so like I said, part of the work you'll do in this chapter will be to work with given probability distributions like this one, and part of it will be for you to figure it out yourself. Okay, let's look at this example. Let's say we have this distribution here, and this time we're looking at number of movies downloaded on Netflix in each month. So, for example, I don't know if you guys are aware, you're able to download content, not just movies, but you're allowed to download content onto your cell phone, for example, or your iPad, so that you can watch it when you don't have Wi-Fi. So when I travel on an airplane, for example, I know I'm not going to have cell phone access, and I could have the airplane's Wi-Fi, but they usually want to charge you. So it just makes a lot more sense while I'm still at home and I have my Wi-Fi to download something so that I can watch it on the plane and not be bothered by things, right? Maybe I download a movie or two. Now, of course, Netflix is going to put some restrictions on there because whenever you allow people to do something, someone's going to take advantage of it. So they don't want you to download 20 movies or 100 movies. So they put a limit on it. So let's say, just for the purposes of this example, that Netflix has put a maximum of 5 downloads, 5 movies that you can download onto your phone in a 1-month period. Okay, and they keep track of all of this stuff. So they look at their results, their computer results, to figure out how many downloads that people have. So maybe this is the distribution that they generate, right? So this would indicate that 6% of all Netflix customers downloaded 0 movies. They didn't even do it, right? And this indicates that 58% of the Netflix customers downloaded 1 movie, right? The possibility that another way to look at this is that if you randomly choose one Netflix customer, what is the probability that one customer downloaded 1 movie in that month? Well, there's a 58% chance that can happen, right? And it's by far the most likely outcome, 58%. Good. This means that 1% of all Netflix customers downloaded 5 movies in 1 month. And then another way to look at this is that if you randomly choose one Netflix customer, what is the probability that one Netflix customer has downloaded 5 movies in 1 month? Well, there's a 1% chance of that. Good. So let's write that, both of those interpretations. Perfectly good, valid interpretations. Both are good. And both of them say, let's go with, say, that one right there. There's two ways to interpret that. This is saying that 10% of all Netflix customers. Okay, so that's one interpretation. 10% of all Netflix customers download exactly 3 movies in a month. Or another perfectly valid way to interpret this is, so the other interpretation is that there is a 10% chance that one randomly selected Netflix customer downloaded exactly 3 movies in a month. Right? So there's two ways to look at it. They're both valid. In some cases, you'd want to interpret it this way, and in some cases, you'd want to interpret it this way. Okay. Let's confirm that it's a valid probability distribution table. Assuming that Netflix puts a cap on the number of downloads to 5, there can't be 6, there can't be 7. So we've listed all possible outcomes. They've downloaded 0 or 1 or 2 or 3 or 4 or 5, no other options. And then we have their corresponding probabilities next to them. Each probability is between 0 and 1 inclusive, so that part is okay. And now we just have to confirm that all of these things add up to 100. Again, you can just get your calculator and do it. Otherwise, kind of group them up where it's easiest. So these two are easy since they add up to 80. They add up to 80. 80, 90, and then this one, and this one add up to 10. Yep, works out. They all add up to 1. So the sum of the probabilities equals 1. That's one of the conditions. Condition number 1, the sum of the probabilities as x goes from 0 to 5 equals 1. That worked out well. And 2, that each probability, f of x, is between 0 and 1 inclusive. By inclusive, we mean that it's allowed to be a 1 and it's allowed to be a 0. Right? 0 just means it's not going to happen, and 1 means it's guaranteed to happen. Okay, so it's a valid probability distribution. And also note that we sometimes prefer to interpret these or present these in a graphical way. So here is a graphical way of representing this exact table. Right? So we have our options for x written along the horizontal axes. So we want to create these boxes, these rectangles, where at the center of each rectangle we identify the value of the random variable. Right? Notice that the little corner over here is not 0, 0, like it normally is, like we're normally used to seeing. The 0 is in the center of this box because this is the rectangle that visually describes for us the probability that x equals to 0. And this is at the center of this box because the area in purple here visually describes the probability that the value equals to 1, the random variable x equals to 1. Notice that the width of each one of these rectangles is going to be equal to 1. Right? So the width of each rectangle is equal to 1. So the distance between there and there is 1. The distance between there and there is 1. Right? There's always a 1. And the height is corresponds to its probability. 1 times any number is that number. So that's why if, for example, for the 1, if this goes up to a height of 0.58, then when we multiply 1 times 0.58, then this area in here, this area in purple, equals to the number 0.58. It's a very subtle distinction that you're changing from a decimal to an area that pretty much gives you the same result. But it's a very important distinction because as we move forward, we're going to want to work with a picture like this or something similar that describes a probability based on an area, right? A picture that symbolically the area in that picture can be used to find probabilities. Okay, all right. So all these areas in purple then are gonna represent these probabilities. So the area of this little box is 0.06, and the area of this box is 0.22, and so on and so forth. So finding the areas of all the purples, if we add up all those areas, they better add up to 1. Good, good, good. Also notice that there is a benefit and a drawback to doing things this way. When you have a table, it's very easy to be very, very accurate. We could just go down to more decimal places if we need to, and we could see them. When you do a graph like this, we do lose some accuracy. Notice that if this table wasn't presented, it would be hard for me to guess that this height there is 0.58. I know it's close to 0.6, but someone can look at this and guess that it was 0.59. Someone can look at this and guess that it was about 0.57, right? And it's hard to maintain that level of accuracy, especially if it turns out that this had more accuracy involved. This was 0.58321. How am I going to describe that in this graph, right? So when we go to graphs, we often lose precision. So that's the drawback. But the advantage is that it's easier to digest. It's easier to notice patterns. So here I can visually quickly see that this one is the most likely outcome, pops up, and then it kind of comes down. And I can see that there's a right tail to this distribution. And okay, maybe that's not such a big deal right now because there's only 5 options. But if we had a lot more options, hundreds of them, it would be hard to stare at a table with hundreds of decimals running all over the place, especially if a lot of them are really small. It's hard to see the patterns and hard to see where the biggest one is, the smallest one is. And so if we see a nice little picture like this one, we might be able to spot quick little patterns out of the whole thing. So that's one of the advantages, one of the reasons we go to these graphs. And also, starting in the next chapter moving forward, again, we're going to have continuous random variables. We're not going to be able to make a list of the possible options because there's an infinite number of them, right? The only reason we're allowed to get away with this is because this is for a discrete random variable, so we can write them down. But when we get to continuous random variables, there's an infinite number of possible outcomes. We're not going to be able to do a table at all, and we're going to have to rely on some sort of a graph that describes that probability distribution. Okay. Also, the last possible way of providing a probability distribution is through some sort of a formula. And so we'll see some examples involving that. But the table as well as a graph like this one are by far the most popular things we work with in this chapter. All right, let's move on. Once we have a discrete random variable, a probability distribution, one of the things we might want to get out of it is the mean of the discrete random variable, and it is given by this formula. Mu sub x, little mean, mu sub x is the mean of the discrete random variable, and it's equal to this formula. The formula equals to x times p of x for each value that x can take on, and then we add them up. Okay, where x is the value of the random variable and p of x is the probability of observing that value. All right, let's explore where this comes from. Let's see if we can come up with some reasoning for this. So let's say, for example, just kind of coming up with a random example here. Let's say that I have a big bag of marbles or little ping pong balls or a jar or whatever this is. Ugly. Okay, so inside here I have several of them. Let's say I have the number 1, the number 2. Now some of them repeat. Maybe I have another one that's the number 2, another one that's the number 3, another one that's the number 3, another one that's the number 3, another one that's the number 3. That's 4 3s, 2 2s. No, let's make it 3 2s. 1, 2, 3, 4, 5 ones. And let's toss in there a 0. Okay, so let's say I have these. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's toss in one more. 1, 4. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 little balls. 15 balls. 15 numbered balls. In a bag. Okay, my experiment, super easy. My experiment is going to be to pick one of those balls at random. I'm going to shake it all up, reach my hand in there, and pull out one of those little balls, right? So shake up the bag, pick one little ball. Okay, so what are the possible outcomes that I can get from this? So let x equal the possible outcomes that I can get. So x could take on several values. So this is like a capital X for the value of the random variable equals lowercase x. Okay, so x could take on a 0, right? I reach in there, and one of the possible things is that I pull out the one that has a little 0 on it. That's a possibility. Or I could reach in there and take out the little ball that has a 1 in it. At this moment, we're not worrying about the probability yet. I'm just saying, I reach in there and I could pull out a little ball that has a 1 in there. Right? We're only doing this experiment one time, so it's not like I'm reaching in there and getting more balls and more balls. I'm about to do the experiment only one time. And I'm just kind of thinking ahead of what are the possible outcomes. Well, it could be a 0, a 1. Of course, it could be a 2, or a 3, or a 4. It can't be a 5. There's no 5s in there. It can't be a -1. There's no -1s in there. Right? Okay, so here are all the possible outcomes that can happen. Okay, so now let's think about what are those probabilities. Probability that x will be equal to a little x. You know what? Actually, yeah, this thing is weird. That makes sense. This is x, and probably the capital X equals x. Okay, so in other words, here we're going to say, what's the probability that my random variable equals 0? Okay, well, going back to our probability chapter, there were 15 balls in that bag, and only one of them has a 0. So I know that that probability is 1 out of 15. Right? Okay. Now over here, all right. So what is the probability that I get 1 out of this bag? Reach in there, pull it out. What is the probability that it's a 1? Well, we said there are 1, 2, 5, 6 little balls that have a 1 in there. So that's going to be our probability. Probability that x equals 1 is equal to 6 out of 15. Good. All right. Probability that x equals to 2. Let's go a highlighter here. That's going to be 1, 2, 3 different ways that we can pull out a 2. So the probability that x equals 2 equals to 3 out of 15. Don't worry about reducing the fractions at this point. Okay, and then what's the probability that x equals to 3? All right, x equals to 3. Let's go with this guy. Well, 1, 2, 3, 4 different ways that the little ping pong ball turns out to be a 3. So this will be 4 out of 15. And finally, the last option is that when you reach in there, you get a 4. And so that there's only one way that can happen. There's only one little ball that has a 4 on it. So that's 1 out of 15. Okay, so we can go to our calculator and turn this into decimals. That's fine, and round it to some amount if we wish, or we can leave them as fractions. The advantage of leaving them as fractions is that when we go to add them, they all have the same denominator. So if I want to add the probability, if I want to find the probability, the sum of the probability of x, as x goes from 0 through 4 in this case, that'll be p of 0 plus probability of 1 plus the probability of 2 plus the probability of 3 plus the probability that we get a 4. Okay, well that's going to be equal to 1 out of 15 plus 6 out of 15 plus 3 out of 15 plus 4 out of 15 plus 1 out of 15. Luckily, they all have the same denominator, so all we have to do is write it as one big happy fraction with a 15 in the denominator, and this is going to be 1 plus 6 plus 3 plus 4 plus 1. That makes it 7, 10, 15. They add up to 15 over 15, otherwise known as 1. So it works out. It satisfies that condition that all of them add up to 1. And like I said, it makes it easier to see it this way when they're written down in fractional form. But we can just take our calculator and easily convert each one of these things. So if we launch our calculator, we get 1 divided by 15 is equal to that, and 6 divided by 15. 6 divided by 15 is that, and 3 divided by 15 is that, and 4 divided by 15 is that, and 1 divided by 4, we already have 1 divided by 15, so we have all the results we need. We could write these using decimals and then, of course, round a little bit. So then we can say that this is approximately 0.067, and this one is this one's exactly 0.4, this one's exactly 0.2, and this one is 0.267 approximately, and back to this one, it's also 0.067. Okay, so now if we add these decimals, they're not going to add up to exactly 1 because of the rounding we just did. So keep that in mind, that they might not add up to exactly 1 because of rounding issues, but the same idea is there. Okay, so now what do we mean by this mean thing? Okay, so now let's figure out what we mean by this whole mean value thing. Okay, so let's go back to my little ball, my little bag of little balls with little numbers on them. What's the mean value of those little balls, right? Some of them are 1, some of them are 3. What's the mean value of all of those little balls? Okay, so what I could do is grab all of those things, add them together, and divide by 15, right? That's the definition of the mean, the arithmetic mean. So let's grab those off to the side. I'm going to zoom out a little bit more. Go over here. So there is a 1. I'm just going to copy those numbers down over there. 1, and then I want to have a plus 2, plus another. Okay, so all I did was add up all of these numbers. I wrote down the summation of all those values. Let's see where they're highlighted. So there was 1, 2, 3, 4 threes. So that's this guy. 1, 2, 3, 4 threes. And there were 3 twos. 1, 2, 3 of them. And there were 4. Let's see. There was 1 red from there, from here, and then another red from there, and then 4 reds. 1, 2, 3, 4, and then a 0 and a 4. A 0 and a 4. Okay, so if I take the summation of all those numbers, I add them all up, and I divide by 15, because that's how many numbers there were total. This is the mean. right? This is the arithmetic mean. Oh, so let's actually find it. The mean is equal to, okay, let's add these up. That's going to be 3, 5, 6, 8, 11, 14, 17, 20, 21, 22, 23, 24, 28. 28 divided by 15. Okay, so I can go over to my calculator and say that that mean is equal to 28 divided by 15, 1.867. 1.867. Right? So that's one way to describe the values in this little bag, right? Some of them are a 1, some of them are a 0, some of them are a 3. On average, the mean value is 1.867. Obviously, none of the balls have a 1.867 on them, but it's a way of describing one way of describing these results, right? It's one characteristic of the values of these guys. Okay, so I added them together, divided by 15. That's how I get that. Another way to do this, though, another alternative thing we could do is just group them up and do the following. I'm going to take this guy right here. I'm going to just copy. Well, I'm just going to start all over again. No, that's fine. Let's put a little. So put or. Consider the following. I could take this. I'll put or. Okay, I could take this exact same little formula, but instead of actually adding them, I could do this little trick thing. I'm going to reorganize them. I'm going to put all the ones right next to each other. So that's 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6 of them. 1, 2, 3, 4, 5, 6 of them. Plus, actually, let's put the 0 out in front so we can go in order. So let's put the 0 out here, plus the 1s, plus there were 3 2s, 1, 2, 3, plus there's 1, 2, 3, 4 3s, 1, 2, 3, 4, plus a 4. And we're going to divide all of this still by 15. We get that. Okay, so now I'm going to regroup them by saying that there is one copy of the 0 plus of the 1s, there were 4 copies of it, right? Because adding up, I'm sorry, not 4, 6 copies. I'm going to put it in, I'll put it in red. There was 1 copy of the 0, and now there were 6 copies of the 1. So 6 times 1 is 6, which is the same as adding up the 1 6 times, plus 2 times, and there were 1, 2, 3 copies of the 2, plus there were 4 copies of the 3. 1, 2, 3, 4 copies, plus, finally, 4, there's only 1 copy of them, right? So I'm just regrouping them. Multiplication is really just a way of regrouping addition. All of that divided by 15. Okay, so if I actually just executed all these multiplications, 0 times 1 is 0, 1 times 6 is 6, 2 times 3 is 6, 3 times 4 is 12, and 4 times 1 is 4, and then I added them together, they're going to add up to that 28. Okay, but we don't want to do that. Instead, we're going to further break this down into the summation of lots of little fractions. So I'm going to regroup them as 0 times 1 over 15 plus 1 times 6 Okay, and then one more little separation. I'm going to separate it as 0 times the fraction 1 over 15 plus 1 times the fraction 6 over 15 plus 2 times the fraction 3 over 15 and notice what we have now. Each of these values, 0, 1, 2, 3, and 4, each of these values is the value of x. And each of these values, the 1 over 15, the 6 over 15, the 3 over 15, the 4 over 15, and the 1 over 15 is the probability of that x value. Right? So this is the summation of x times p of x. Right? It's going to be the value x equals 0 times the probability of 0. Let me rewrite that this way first of all. So this is 0 times the probability that x equals 0. That's this. And we want to add it times 1 times the probability that x equals 1. That's what this is. The probability that x equals to 1 is 6 over 15. Plus 2 times the probability that x equals 2 plus 3 times the probability that x equals 3 plus 4 times the probability that x equals 4. Right? So what we have is each of the x values times its probability. That's what this means. The probability, the sum of x times p of x, as x in this case ranges from 1 to 4. Okay, so what does that mean in terms of our table? Let's go back to our table. It means that if we take each one of these x values and multiply it, let's go back to this guy. We take each one of the x values and we multiply it across with its probability, the probability that x will take on that value, multiply them across and add them down, that will be equal to the mean value of our experiment. Good. That is what we call the mean random variable. Good. And that's where this formula comes from. The mean of discrete random variable is equal to x times p of x, going across and adding them down. Here's an example. Compute the mean of the discrete random variable that we worked with earlier involving the Netflix, right? So number of movies downloaded by people. 6% of the people out there downloaded 0 movies. 58% of the people, customers of Netflix, downloaded only 1 of the movie. Now I know this talks about persons renting things, but I've just switched the little story to be something a little more relevant since nobody knows what a DVD is and nobody rents them. But we download things onto our cell phone, so we could either download 1 movie to watch off network, or 3 movies to watch off network, or 0 movies, or so on and so forth. So what is the mean value? Okay, so we got to multiply across and add down, or 0 times 0.06, 1 times 0.58, 2 times 0.22, 3 times 0.10, 4 times 0.03, 5 times 0.01. Multiply all that together, add them together, and there we go, we get this, 1.49. We can also do that with our calculator, so let's recreate that process with our calculator. Go to Stat, go to Edit, we're going to need two of these columns. So L1, clear, enter. L2, clear, enter. So let's practice a few things we're going to need. So let's duplicate that table onto our calculator. So 0, 1, 2, 3, 4, 5, 6. Oops, not 6. Delete that one. Okay, so then the first one is 0.06, enter. 0.58, enter. 0.22, enter. 0.10, enter. 0.03, enter. And 0.01, enter. Okay, so I have recreated that table onto my calculator. And now what I want to do is multiply them across and then add them together. That'll give me this number here. To do that, I'm going to do column operations. I'm going to go over to L3, use your arrows to highlight the L3, and then I'm going to make L3 equal to L1 times L2, just multiplying them across. Enter. So 0 times any number is 0. 1 times 0.58 is 0.58. But 2 times 0.22 is 0.44. 3 times 0.1 is 0.3, and so on and so forth. And now I need to add up these values. So remember that if we do a one variable stat on L3, it'll give us everything we ever wanted to know about that list, including the sum, which is what we're interested in right now. So we're going to hit stat, calculate, one variable statistics, hit L3 on here to get all that information we need there, hit calculate, and that gives us everything we need, including the sum of the values on list 3, which is 1.49. That's what this is. It's the mean of that discrete random variable. Good. The mean of the discrete random variable is 1.49. Okay. Interpretation. What should we make that? How should we think about that when we figure out the mean of discrete random variable? How should we interpret that? Suppose an experiment is repeated n independent times, and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of n trials will approach mu sub x, the mean of the discrete random variable, the mean of the random variable x. In other words, let x sub 1 be the value of the random variable x. After the first experiment, x sub 2 be the mean value, be the value of the random variable x after the experiment a second time, and so on and so forth, so on and so forth. Then x sub bar represents the sample mean of the first n experiment outcomes. So we add up all the outcomes, divide by n. That'll give us that that sample mean. And so we say that that sample mean will get infinitely close to the random variable, the mean of the random variable mu sub x, will get infinitely close as n increases to infinity. Or we say that the difference between the two gets close to 0 as n increases. Okay, what does that mean? Let's go back over here to this thing. Let's find an interpretation, or let's see what that means for this guy. This is saying that if we start randomly picking Netflix customers, the first customer, we randomly stop and said, hey, how many DVDs did you rent or download to your phone in 1 month? Okay, the first person says, I did 1. And then we randomly select another person, and that other person says, I did 5. Okay, so this is the result of 1. This is the result of the second experiment. If we take a mean, a running mean right now, the mean after 2 of these, well, we add them together and divide by 2. The mean at this point is just 1 plus 5 divided by 2, which equals to 3, right? As of right now, it equals 3. Okay, we stop somebody else again and figure out, hey, excuse me, how many did you download? And the next person says 2, and the next person says 2, and the next person says 0, and the next person says 1, and the next person says 4. Okay, so now I've done 1, 2, 3, 4, 5, 6, 7, and let's say the next person also says 0. So now I've surveyed 8 different people. At this point, my running mean at this point would be equal to the sum of all of those values, which would be 1 plus 5 plus 2 plus another 2 plus 1 plus 4, and then I could put in the plus zeros, but that is not really necessary, right? And we divide that by 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's going to be 6, 10, 15 divided by 8. 15 divided by 8. 15 divided by 8 equals 1.875. Equals 1.875. Okay, so this is kind of like the running mean. If I keep going, and I ask another person, how many movies did you download? 0. Maybe another person says 1. Maybe another person says 1. 1 is probably going to be a very common answer, right? Looking at my table, 1 was the most popular answer. 58% of all Netflix customers downloaded 1 movie in a month. Or another way to look at it, if I randomly select one customer, there's a 58% chance that they're going to tell me the answer is 1. So 1 should be a very, very popular answer that we get, okay? So let's say that I do this a few more times. Maybe I get a lot of 1s and I get a couple of 2s in there. 1, 2, 3, 4, 5. Okay, so I find the new mean after I've done this, including 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this time I'm going to divide it by 13. And I'm going to add up all of these numbers. This time they add up to, well, it used to be 15 up to there. 15 and another 3 gets me to 20. And if I divide that, that's going to be 20 divided by 13. That's going to be 1.5, 1.5384. Okay, so if I keep going on like this forever, I keep drawing people in, I keep asking them, and every time I ask more people, I come up with a new sample mean, right? As I keep asking more and more people, as this, the number of people I ask grows toward infinity, as this number gets bigger and bigger and bigger, and I constantly figure out this mean, the running sample mean, the running sample mean will get infinitely close to that value that we found, the mean of the random variable. In this case, for us, we're saying that as this, the number of people I survey increases toward infinity, that running total of the sample mean will get infinitely close to the 1.49. That's what that means. When I did it for 2 people, it was way off. It was 3. When I did it for 8 people, it was still pretty off. It was 1.875. When I did it for 13 people, it got a little closer, 1.53. And as I keep going forever, if I keep drawing more and more people, the more people I get, the total running average of the people I've gotten, that X bar, the sample mean, will get closer and closer and closer to this calculated value, which is the mean of the discrete random variable. Right? That's an interpretation for that. A visual of the exact same thing is presented right below here. So let's say that this table represents the exact same thing I just said. So in other words, this means one person was randomly selected. They said, I downloaded 1 movie. I downloaded 1 movie. Another person says, I downloaded 1 movie. So 1 is a very popular answer, right? And then somebody says, no, I downloaded 2, I downloaded 2, I downloaded 2, 2. No, I downloaded 1, I downloaded 1, I downloaded 1. Okay, I can come up with the running means of these things, right? So let's describe those running means. The very first one I get, well, it's just going to be based on 1 person. So that's just going to be 1. And then I calculate it again after I have 2 people. Well, that's still going to be 1. Actually, I think that this goes down. You know, I'm not sure if they mean it to be this way, because otherwise it's going to be, yep, that's what they mean. Okay. Okay, so let's calculate the running means, and let's interpret these kind of coming down. So this is person number 1 said that they downloaded 1. Based out of 1, the mean is 1. Okay, and then the next time I recalculate the running mean, I've asked 2 people, right? Going up to and including this person. So if I've done this person, that's just the 1. But now I want to include 1 and 2. That's 2 people. So I add them together. That's 3. 3 divided by 2. This becomes 3 divided by 2, which is equal to 1.5. Okay, the running mean, including those 2 people, is 1.5. And then I calculate it again. And the mean, going up to the first 3 people, well, that's going to be 4 divided by 3. 4 divided by 3, which is equal to 1.33333. Okay, then I keep going. The mean going up to the first 5 people, sorry, something is wrong. 4, sorry. The mean up to the first 4 people. Well, adding a 0 didn't change anything, so that's just going to be 4 out of 4, which gets us to 1. Okay, then the next one, including up to 5 people. Now I asked another person, they said, no, I rented 1, I downloaded 1. So that'll be an extra 5 out of 5, which still gives you 1. And then the next one is going to be 6 out of 6. So that still gets you to 1. So you're up to there. And then the next person says 0. The next 2 people say 0, in fact. So the next one is going to be 6 out of 7. That gets us up to here. Right? In other words, let's double check that all these numbers add up to 6. That's going to be 3, 4, 5, 6. And then the 0 didn't do anything, but it's out of 7 numbers. So 6 divided by 7 equals to 0.8514. Let's just say around 86. And then I keep going, and the next one I calculate is going to include yet another 0. So then that's going to be 6 out of 8. Which is equal to it's equal to 0.75. Then the next one, okay, so then we include that guy. And the next one is going to be x bar is going to be 11 out of 9. Which is going to be 1.22. And finally, the last one in this list, at least, in the first column, is going to end up giving us up to 13 divided by 10, which equals to 1.3, right? And that covers up to the first column. Next, we'd go, okay, well, this just means that another person was asked, and the next person said 1. So going to the next column, the running total then, I'm just going to put it up here, would then be, well, 1 more gets us to 14 divided by 11, which equals to 14 divided by 11 equals to 1.27-ish, something like that. Right. And this is the, including the green one, which means that there's 11 people. Okay, well, we can just keep going. And now let's graph these, or let's see what it looks like to graph these. These are going to be ordered pairs, where this means that there is one value associated. So this is going to be the ordered pair 1, 1, and this is going to be the ordered pair 2, 1.5, and this is going to be the ordered pair 3, 1.33, and this is going to be the ordered pair 4, comma 1, and then the ordered pair 5, comma 1, and so on and so forth. Okay, so if we graph all these ordered pairs, they'll look like this. It's a little hard to see, but the very first one was a 1, and then it went up to 0.5, and then it went down, and then it went down, and it went down, and then it went way down, and then it went down, and then it went up, and then it went up. So this is kind of like describing the first few values that we got. And if we had kept going in that process, we'd see that then we'd end up getting these, and then these, and then these, and these, and these, and these, and these, and these, these, and these, and these. And then if we really got silly here, after 50 of those numbers, looks like we'd end up somewhere around there. And then it started to climb up a little, and then it kind of came down, and then it went up, and then went up. And then eventually, after 100, it got pretty close to the value of the discrete random variable. Remember that the value of the discrete random variable, mu sub x, was 1.49, right? So just below, well, that bar right there, just below this level. And as you can see, it's as the number of trials increases, the graph that describes the ordered pair, which describes the number of trials, comma, the running mean based on those number of trials. Right, that's what these little dots are. These ordered pairs are those. We calculated the first like 11 of them. But as you can see, as we keep going, they're gonna get eventually really close to the expected value of the discrete random variable. Keep in mind that we're not saying that it's gonna eventually equal that and then stop. Right? This doesn't ever stop. You can just keep going with your trials. Why stop at 100? Do 200, do 300, do 500, do 1,000, right? And so you're never going to stop, and it's never going to just be equal to 1.49 and then be done at that point. No, it's just going to get infinitely close to it, always infinitely close to it. Might actually be equal to it at some point, but then you keep going, and then it might move to something else. Notice that early on, the very second value that we calculated was 1.5, really close, but then it went away from that. Then we went way, way below that, and then back up, and so on and so forth, right? So the law of large numbers indicates that as n, the number of trials, goes toward infinity, as we get more and more and more of these values, then this running sample mean is going to get closer and closer and closer to the expected value. It might at one point be equal to it, but very often you don't really know what the real answer is, so you never really know when to stop. You just have to let this go on for a very long time and see what the pattern is and where is it approaching. Okay, so hopefully that makes sense. So because the mean of the random variable represents what we would expect would happen in the long run, it is also called the expected value of the random variable, right? Denoted by E of x, the expected value of the discrete probability distribution. Okay, moving on. So this is a classic example from this section. Consider the following scenario. A term life insurance policy would pay the beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose that a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. According to the National Vital Statistics Report, Volume 47, Number 28, the probability that a female will survive the year is equal to 0.99791. Compute the expected value of the policy to the insurance company. So it's important to keep track of who you're working for, right? You're working for the insurance company. So when you write down the values, the money, you got to put it in terms. You got to make sure that the signs of the money are associated or are in the right perspective. So money coming into the company, money they're making, is usually considered to be positive, whereas money that the company is paying out, giving away, spending it is considered negative. And that's opposite to the person that's getting the policy, right? So the person that's buying the policy, this is negative because they're paying $530. But then if they do die and their next of kin receives money, then this would be positive. Whereas from the company's perspective, it's the other way around. 530 is positive, that's coming in. Whereas if they ever have to pay out money, somebody passes away, then this quantity would be the negative. Okay, so they want it from the company's perspective. So from the company's perspective, well, either they have to pay out this big fat check here, or they just receive money. If the person just lives, they survive, that means that they give you $530. That's a positive result. And on the other hand, if they have to pay out money, well, they pay out a check for $250,000. However, that's not entirely what they're losing because they've already received the initial 530. So we would subtract the 530 from the 250,000 to give you 249,000. Let's put it in another color. To give you $249,470. Right, that's what they're actually losing because they did receive a little bit of money. And then let's look at these probabilities. There is a very high chance that they're going to live. There's a 99% chance that this person will survive the year. And therefore, this is that probability means that that's the probability associated with this outcome. So that's going to be 0.99791. Whereas the likelihood that that doesn't happen is going to be its complement. Its complement is going to be 1 minus 0.99791, which is equal to 0.00209. Okay, so this is the probability that this happens. This is the probability that that happens. And now we have to be careful about the signs, right? So this is from the insurance company's point of view. So from the insurance company's point of view, this is positive money. This is positive money. Whereas this is a negative, right? They'd have to pay that out if somebody passes away. So from their bookkeeping perspective, this is money going out and this is money coming in. Okay, next, to figure out the value of the discrete random variable, the mean of the discrete random variable, let's come up with a new column over here where we figure out x times px. We want to multiply across and figure out what this is. So if we multiply 530 times 0.99791, we get $528 with 89 cents. And if we multiply these across, keeping in mind it's positive, now this is going to be some negative number, and it's going to be 249,470 times 0.00209. Rounding off to the nearest penny, I get minus 521.39. And now if I add those up, keeping in mind that this one is a negative, so really it's this one minus that one. So it's going to be 528.89 minus 521.39, and we get 7.50. This is 7.50. That's the value of my discrete random variable. This is the value of mu sub x. Good. Let's see if that's what your author did. Looks a little neater, I'm sure. Yep, 7.50. Okay, so 530 is what you have to pay to get this policy. There's a 99% chance that you're going to survive the year. If you don't survive, then the company has to issue out a check, and this is how much they're going to lose. The check is for this amount, $550,000, but they have already accepted $530. So really, they're only losing $249,470. So it's a negative. Multiply this times this times that. That's how we get this equation down here, and that'll be our expected value. Same thing as the mean of the discrete random variable, right? So another way of saying this is mu sub x is the same thing as the expected value of x, which in this case is $7.50. Okay, what's the interpretation of this? How can we interpret what that number means? Okay, well, picture it this way. You work for this giant insurance company, and you're just processing, these accounts. So as you process the accounts, see what happened. Maybe you see that one person, they paid $530, and nothing happened to them, right? At the end of the year, they're fine. Nothing happens. So the company just gets to keep that. Then another person, all right, then they just live. They're fine. Another person, they just live. They're fine. So if I kept track of this sort of running average here, so far, it looks really good. After 3 customers, the average is just going to be the sum of these 3 divided by 3. Well, it's just going to be 530, right? Okay, let's say that the very 4th customer of the year, no good. They passed away. That means that even on the 4th try here, they had to pay out a check and they lost this amount of money. So after just 4 customers, what's my running mean going to be? Well, it's going to be equal to 3 times 530 positive minus 249,470. And that we divide by the 4 customers that we had. And so my mean would be equal to 3 times 530 minus 249,470 divided by 4 minus 61,000 minus 61,970. Right? What does that mean? On average, for the first 4 customers, on average, the company's losing $61,000. It's very it doesn't provide a good picture of what's happening, because really it's like they made a little money, they made a little money, they made a little money, and then they lost a lot of money. But the average of all these 4, the mean of all these 4, at this point so far is minus 61,970. They've only had 4 customers, so if you take all the money they lost and divide it by 4, on average they're losing $61,970 per customer. Per customer, right? It's not good. Okay, but it's the insurance biz. You keep going. All right, the next customer comes along, and that person is fine. And then the next person, and that person is fine. Most of the time when they issue out a policy, it's easy money, right? They just get the money and nothing happens. I have life insurance. Every single month they just take my money, and I haven't died, so it's just money they take. Every day, every single month, they make a nice profit off of me and don't really have to do anything, right? They only have to do something if somebody actually dies. So let's say that at this point now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 customers have gone by. Now we want to figure out that mean. What's the mean after 10 customers? Well, 9 of them were fine. 9 of them, they just made $530. It was just that one person that died. And so if we figure out what that is, we'll figure out the running mean with the first 10 customers. So that'll be 9 times 530 minus 249,470. And then all of that gets divided by 10. So now we're down to 24,470. So now this is minus 24,470. Okay, so when we were looking at the mean after 4 customers, the mean was a very big negative, right? Because they had to pay out one big check. So with the first 4 customers, on average, they were losing $61,970 per customer. But after we extend this out and go, okay, wait a minute, let's look at the business after a few more customers. Now we got the first 10 customers. And if we take our losses, which is really just this, by and large part this, if we take our losses and divide it by the number of customers, so at this point, we're really losing $24,470 on average per customer. Right? And again, that's misleading because you think, oh wow, every single customer you're losing money. Not really. It's that you make money, you make money, you make money, you make money on a lot of people. It's just the one time when somebody died, you paid out a lot of money. Okay, so that's the running mean. So what we want to say is that if we keep going, right, we keep going, we get more and more customers. As the number of customers increases, we got another 530, we get another 530, you know, lots of 530s. Maybe somewhere in there might be another, you know, another death. So another time we're going to have to pay out 470. But there's also going to be another 530 and another 530 and so on and so forth forever as we let that number grow, right? As the number of customers grows toward infinity, as n grows toward infinity, and we're constantly keeping track of this mean, right? The mean stopping there, right? And then the mean stopping there, and then the mean stopping, right? So as n goes to infinity, that mean, the running mean, is going to approach the expected value, which in this case we saw was going to approach $7.50. So it means that on average, the company is going to profit $7.50 per customer, as long as we have a very, very large pool, right? As long okay. So as long as the insurance company has a very large pool of customers getting this policy, right? It won't be valid if they only sell 10 policies, if they only sell 20. We got to think of them selling thousands and thousands of these policies. So as long as they have a very large pool of customers buying this policy, most of them will live. Therefore, the company just gets to pocket $530. Some of them will die, meaning that the company will pay out $247,470. But on average, the company expects to make about $7.50 per customer, right? Some of them represent a $530 profit. Some of the individual customers represent a loss of $247,470. But on average, they expect a profit of about $7.50 per customer. I know it's a profit because the expected value is positive, and we did this from the perspective of the company, right? So money coming in is positive, money going out is negative. So if this turned out to be a negative number when we did our calculations, if it was a negative number, that would mean that the company expects to be losing money on average, not making, right? So of course they want to be making money on average. And remember, this is on average per customer. So this isn't exactly what they make for the year. You got to multiply this by the number of customers, assuming that there were thousands or even millions of customers. Then that's how much money they expect to make profit out of this system. Okay, so hopefully that gives you a pretty good idea of what the expected value means. Okay, the final thing we're going to deal with is finding or computing the standard deviation of the discrete random variable. Okay, so the standard deviation of the discrete random variable x is given by, and well, this is the formula that we're going to use. This one is equivalent to that one, but it's what they considered a shortcut back in its day, right? Before there were computers and calculators to help us out, we had to do all of this by hand. It was really difficult to do that. So they, would come up with mathematical equations that are equivalent, but just a little bit easier to work with. But the reason I'm not a huge fan is because the original formula makes it a little easier to see where it comes from, like the meaning of it. When you use algebraic properties to find an equivalent one, you kind of lose track of that meaning. So here, I think we can make sense of what this means. We're going to take each value in our discrete random variables, each value that it can take, and subtract it from its mean. So that's the distance each one is. So we'll talk about that. But once we square it, what does this mean visually? What does that mean? So we kind of lose track of that. And because we don't really need shortcuts, we have technology. So we're going to use technology to simplify our life, and we don't have to do so much arithmetic, just like we did before in Chapter 3. So we're going to do column operations again with our calculators to be able to apply these formulas. And then we'll be able to get it from there, right? Okay, so as you do your homework, keep in mind that the Help Me Solve This might be pushing you to this formula, but we don't use it. So go to your book and make sure you use this formula when you're asked to calculate the standard deviation of discrete random variable. Okay, so we're going to use this formula. In fact, let me, come on. So in the book, but don't worry about that one. Okay, so this is where x is the value of the random variable, and then mu sub x is the expected value or the mean of the random variable, and then p of x is the probability of observing the value of the random variable. Okay, so applying the formula is really not going to be that hard once we use our calculator and column operations to do that. So let's look at this example again. Back to our good old Netflix, right? So here's our discrete random variables. So this is the values that x can take on. These are the probability associated with each one of those values. And then from the work we did above, we found out that our expected value, or the mean of the discrete random variable, is 1.49. So this is what we need to do. Let's create a big table. Big table where we're going to have each one of these values. Right, so following the steps that I need for this. X minus mu sub x squared times p of x. Okay, so that means that this, put it in color, this is going to be 0 and 0.06, and this is going to be 1 and 0.58, and this is going to be 2 and 0.22, and this is going to be 3, and this is going to be 0.10, 4 and 0.03, and 5 and 0.01. Okay, now I need to take each one of these values of x and subtract the value of mu sub x, which was 1.49. I want to take each one of these and subtract that. I know that this first one is going to be negative 1.49. And I know that the next one here, well, that's going to be this one minus that. That's going to be negative 0.49. And so on and so forth. Okay, but I want to do this with my calculator. So let's go on to my calculator and upload all of this onto it and be able to do hopefully be able to do our results in there. Okay, calculator, stat, enter, let's clear out, clear, enter, clear, enter, clear, enter, clear, enter, clear, enter. Okay, so on list 1, I'm going to put these values. I'm going to make list 1 this guy, and list 2 this guy, and then I'm going to make list 3 this guy, and list 4 this guy, and finally we're going to make list 5 this guy. Okay, so this is going to be 0, 1, 2. Good. Okay, so now for this third column, I'm going to take each one of the values in list 1 and subtract 1.49. So I'm going to make list 3 equal to L1, all the values in list 1, and I want to subtract 1.49 from each of them. Let's go back over here, go back to L3, and we're going to do L1 minus 1.49, enter. Okay, so that gives me these values right in here. Okay, so let me just copy those down. That's going to be positive 0.5. Okay, next I want to go over to list 4, and I want to make list 4 equal to list 3 squared. I just want to square each one of these numbers. L sub 3, and I want to make sure that this guy gets squared. Okay, so I'm going to go over to list 4, go up there, and that's going to be equal to list 3 to the power of 2. Good. List 3 to the power of 2, which then gives me 2.2201 and 0. Okay. And then finally, we want to be able to multiply the values of list 4 times L2, right? We want each one of these probabilities times the difference of each value of x minus the expected value squared. So it's going to end up being a little equation where I let L5 equal to L4 times L2. Good. Okay, so that's going to be over here, go this way, go up, and that'll be L4 times L2. Enter. And that'll give me all of those decimal values. Let's copy those over here. So that'll be 0.1332. Okay, so the final step here is that we want to add all of these guys. We want to find the sum of all of these. So that's going to be the sum of list 5. So we know that magical button. Let's go over here to stat, calculate one variable statistics on list 5. And that'll give us anything and everything we ever wanted to know about list 5, including the sum of them. That's this guy right here. The sum of all of these values is equal to 0.8699. So the sum of all of these is going to be the 0.8699. And that is equal to this. Let's go back to our equation so far. That's equal to this thing in here. So now the standard deviation is going to be the square root of that. So what we found so far is then the variance. Remember that if we square the standard deviation, we get to the variance. Okay, so let's look at the formula. So this guy is equal to the sum of x minus mu of x squared times p of x, as x ranges from 0 to 5 in this case. And then we want to take the square root of all that. Okay, well, after all that calculator work, we figured out that this part on the inside is equal to the 0.8699. So if we take the square root of that, then that's going to be equal to our answer. Okay, so this is going to be the square root of 0.8699 is equal to that guy, which then gives me that the standard deviation of the random variable is going to be 0.9327, or approximately that, right? Depending on how you want to round. Okay, let's zoom out a little bit and take a look at this. Okay, so here's the formula that I was following. I did column operations this way, and I was able to figure it out. And I think the author does the exact same thing. Let's see if it matches what they did right over here. Yep, exactly the same thing with columns. They might have done it a slightly different way, but almost the exact same thing. All right, let's take a look at this example from chapter 6, section 1, and this is problem number 32 in your book. Okay, so this is how it's written in the book. SAT test penalty. Some standardized tests, such as SAT scores, incorporate a penalty for wrong answers. For example, a multiple choice question with 5 possible answers will have 1 point awarded for a correct answer and 1/4 point deducted for an incorrect answer. Questions left blank are worth 0 points. Okay, so part A, find the expected number of points received for a multiple choice question with 5 possible answers when a student just guesses. Okay, so part A, what we want to do is create a discrete random variable for the number of points, right? So let x equal the number of points. Okay, so if we create a table for that, x, well, we can see that sometimes you can earn 0 if we leave it blank, or you can earn 1 point if you answer it correctly, or they deduct 1/4 of a point, right? So we'll represent that by minus 1/4 if you get it wrong, right? So that's what these things mean. This one's a blank, you get 0 points. Correct answer, you get a point. And then wrong answer, they deduct a -1/4 of a point. Okay, well then now we got to figure out the probabilities associated with each of these probabilities. So the probability that we want to find all of these, probability x equals 0, probability that x equals 1, and the probability that x equals -1/4. Okay, well, they did say that this student completely guessed, just randomly guessed, and there were 5 options in each question, right? For each question, there are 5 possible answers, and they guessed, assuming there's only 1 correct answer in those guesses, right? So let's say question number 1, question number 2, question number 3, and there's an A, B, C, D, E, right? 1, 2, 3, 4, 5. 5 possible options. In reality, there's only 1 possible correct answer. Maybe the correct answer was B. B was correct. But, you know, you don't know that as a student taking this, and if you're randomly picking, just randomly pick one of them, there is only a 1 in 5 chance you get it right. So if you're randomly choosing, there is a 1 in 5 chance you get it right. However, there are 4 wrong answers that you could choose. So there is a 4 out of 5 chance that you get it wrong by guessing. Now, what's the probability the student guesses? Well, they didn't really give us that kind of information. That's okay though, because in order to figure out the mean standard, the expected value of this variable, we have to multiply across, and it doesn't matter what that is, because when we multiply across, we'll end up with 0 times whatever that is, which equals 0. So it doesn't really matter how often the student guesses. So in other words, how often they leave it blank. So if they leave a question blank, they get 0. And now, how often do they get one correct? If they're just guessing, There's a 1 in 5 chance that'll happen. So when we multiply across, we'll get 1 times 1/5, which equals 1/5. And then when we multiply across, the probability that they get it wrong, if they're just guessing, is going to be negative 1/4 times 4/5, right? This is x times p of x. Good. And now if we add them down, well, okay, let's simplify these. These guys cancel, and that results in just negative 1/5. And so if we add these down, we get 0 plus positive 1/5 plus negative 1/5. The whole thing equals 0, right? So the expected value of the random variable equals 0, right? Okay, so that's per question. So my expected value over a long run, I expect that on average, students will earn about 0 points per question. So if there were 5 questions on this test, right, expected number received for multiple choice question with 5 questions, 5 possible answers when a student guesses. Oh, I thought it said how many questions were on there. 5 possible answers. Okay, anyway, so our expected value is going to be 0, right? And that's the perfect result that you would want. Because if someone's just randomly guessing, you would want them to score 0. Whereas someone that leaves a bunch of them blank because they are acknowledging they don't know it, and only answers the one they know to be true, they should get a higher score, right? So if you're looking at a test and somebody says, you know, here is the test results, question 1, question 2, question 3, 4, 5, 6, 7, 8, 9. So let's say there's 10 questions. You know, one student might stare at several of these and decide, I don't know how to answer them, I don't get it. So maybe they correctly answer this one and this one and this one and this one. So they should get 4 points. And they leave the rest blank because they don't know it. So that person should get 4 points, acknowledging that they definitely understood 4 out of the 10 questions. On the other hand, a student that has 3, 4, 5, 6, 7, 8, 9, 10. A student that also knows the same questions, let's say this one, and then this one, and then this one. So those are the ones they know for sure. They know them. They're not guessing. They know those. But then they decide to come in here and just guess at a bunch of stuff. You know, guess that one, 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 and guess that one. If there are no penalties for guessing, we're just guessing a bunch of stuff, then they might get lucky and get at least 1 or 2 of these correct. And then this person that just guessed a bunch of stuff might get the original 4 points for what they actually know, plus whatever points they get for guessing. And that's not fair, right? This person would score a higher score just because they guessed a bunch of stuff and maybe they got lucky. And so that's why the geniosity of this system punishes people for guessing. And you want to choose a punishment that kind of balances out with the likelihood that they get something right. So if the odds of getting 1 point out of a guess, you know, if there is a certain probability that they get 1 point from guessing, we want the rest of them to give you a penalty which is going to balance out with the point that you got for guessing it correct. And hopefully, if the minus deductive points work out well, a person that guesses gets the same score as the person that doesn't guess, right? Because, you know, they might get 1 or 2 of these correct, but they're also going to get a bunch of minuses, and the minuses and the pluses hopefully will kind of on balance cancel out and give you the same score. However, there's always an element of luck, right? They could guess a bunch of stuff correct and they could get lucky, or they could guess all of them wrong and then just get a bunch of minus points and then end up getting a bad score, right? So that's how this works out. All right, let's go back to our question. Did we answer everything? Part A, find the expected number of points received for a multiple choice question when the student just guesses. Okay, so we got the answer was 0. Explain why there is a deduction for the wrong answers. Okay, so hopefully we did a good job of explaining that. What if, let me just twist this around a little bit. Let's do the exact same kind of question, except let's just say that I just want to do it with a different number just to make sure people can follow what's happening. What if the deduction was more punishing than just this one? The deduction wasn't 1/4. Let's say we really want to punish people for guessing, and we deduct half a point. Every time you guess, we deduct half a point. Okay, so now let's calculate the expected value under these conditions. So again, we want to create a table that has our values for x, so if you leave it blank, you get a 0. If you guess correctly, you get a 1 point. And then you guess incorrectly, you get it wrong, they deduct half a point instead of a quarter of a point. Okay, so then again, if there are, let's change this again. Let's say that there weren't 5 possible choices. Let's say that there were 8 possible choices. With 8 possible choices, okay? So when you're looking at your test, question 1 has A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes for each individual question. Okay, so if you're guessing, right, there's only going to be one correct answer. Let's say that the correct answer was B, right? You didn't know that, but the correct answer is B. And if you're just guessing, that means that there is exactly 1 out of 8 chance of getting it correct. Probability that x equals 1 is equal to 1 out of 8. Okay? So if you guess and you guess wrong, let's say that in that case, the probability that x equals to -1/2, well, there's 7 ways to guess wrong, 7 out of 8. So it's a pretty good chance you're just going to guess it wrong if you're just randomly guessing. And again, in this scenario, it's not really described what the likelihood is that the person leaves it blank. So we'll leave that as an unknown probability. But it doesn't matter because you're getting 0 points for a blank one. If we choose a different value here other than 0, then this would become an issue. But it's not an issue right now. Okay, so then we can find x times p of x. And multiplying across, that's going to be 0. Multiplying across, that's going to be 1/8. Multiplying across, that's going to be equal to -1/2 times 7/8, which equals to -7/16. Good. And so now as we add down, we'll end up with 1/8 plus -7/16 and plus 0. Common denominator is going to be 16. Multiply that by 2/2. So that gives you 2 plus -7 gives you -5/16. That is not a good score. So someone that takes the attitude of, I'm just going to guess my way through this, is expected to have 5 divided by 16, -0.33. -0.313125, right? So on average, this is what we expect they will get in terms of their points for just guessing their way through all of them. Good. So, for example, to interpret what this number means, let's say that there were 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that there were 10 questions on the test. Now, on some of them, the student is not guessing. On some of them, they just know it. They just know number 3. They know it. They know they're going to get 1 point for that one, right? And they know number 8. There's no guessing there. They know that this one is going to be 1 point. They know that one. Maybe they leave a couple blank ones. Let's say that they leave number 1. Let's say that they decide they're not going to guess on that one. They're going to leave it blank. Blank. And they leave that one blank. Okay, and then they decide to roll the dice and guess. They're going to guess on this one. Complete guess. Just a random guess. A, B, C, D, eeny, meeny, miny, mo. Or maybe they take like a little dice. As a student, I sometimes took a little dice on my tests. You know, comes a point where like, I have no idea. Just roll a little dice. Okay, the dice says it's number D. Okay, so what kind of a test result do I expect? Well, the expected value of the guesses is going to be this number on average, right? Sometimes it could be right. Maybe they guess it correctly, right? Sometimes they guess it and they guess it correctly, and they might get a point. And sometimes they guess it wrong and they deduct a half a point, right? And that's for all of these. Sometimes they guess it right. Sometimes they guess it wrong and they get a minus deduction. Sometimes they guess it right. Sometimes they guess it wrong. So all the guess ones, if I do an average, you know, on average, what happened with the guesses? On average, I expect it to be about that per question. And I guessed on 1, 2, 3, 4, 5, 6 of them. So if I multiply 6 times negative 0.312825, that's how many points I expect to get from all the guesses, right? Which is obviously not good, right? That'll be times 6. That's equal to negative 1.875. Now add to that the ones I actually knew. I did know these two, so I expect to get plus 2 points from the ones I did know. And there was a couple I left blank, so I get zeros from that. Plus 2 plus zeros for the blank ones, which means that my statistically expected result is going to be to have a score of my statistically expected result is that I'll get a positive 0.125 from this. Right? Compare that to a different student that decides not to guess at all, answers the 2 questions they knew, and leaves everything else blank. Well, that student is expected to get a 2 points. Right? They knew 2 of them, they left everything else blank, they get a 2. This student, on the other hand, that decided to guess a bunch of stuff, statistically, I'm expecting that these guys, the ones they guess, they're going to get, on average, negative 0.3125 per question, on average. And there were 6 guesses, therefore they get this. They could get lucky, right? It could be a very lucky student that just guessed it right, guessed it right, guessed it right, guessed it right, and then just gets a bunch of points. Maybe they do much better than the student that just left everything else blank and just wrote the 2 that they didn't know how to do, but it's unlikely, right? The most typical statistical result will be that on balance, they get an average of negative 0.3126 per guess that they got incorrect. So this is the test result that I expect for a student that does this. Okay. Hopefully that gives you all and everything you need to be able to do your homework from section 6.1. As always, send me an email if you're having trouble with any one of the questions in our homework. Good luck.